when we talk about respiratory care, there's just fundamentals you have to know. And what you have to know, and I didn't write it on the board, but let's just go through this. 1 atmosphere. The air that we inhale is 1 atmosphere. And you'll see why I talk about 1 atmosphere, because we're going to get above that. So we're talking about 1 atmosphere, and if you will, that's sea level. It's 1 atmosphere. And this will make a little bit more sense to you in Module 2 when we start talking about hypoxia. So for right now, you just have to take my word and the book's word. 1 atmosphere. It's at sea level. Now this P, anytime you see a P, just like the P on a PaO2 and a PaCO2 is pressure. And this subscript B is barometric. Baro means pressure, and metric means it's in the metric system. Somebody asked me why was the units important or something. And I told you either yesterday or Monday that most of everything we use is in the metric system except for 1 or 2 things is English. So this is the metric system. 1 atmosphere equals 760 millimeters of mercury. You need to know that. Come back here. Okay, if you can't see, come back there.
How do you spell barometric? B-A-R-A metric?
B-A-R-O metric.
Okay.
So 1 atmosphere equals 760 millimeters of mercury. And then in English, it equals 14.7 psi, pounds per square inch. So this is English. And this is barometric. So 1 atmosphere can equal 760 millimeters of mercury, and it equals 14.7 psi. But most of the time we don't use this. We use that. Okay? And then this STPD, this is standard temperature. Standard temperature, pressure, dry. And so what's standard temperature? Standard temperature based on this, as well as our equipment, is about 70 degrees Fahrenheit. The pressure is 760 millimeters of mercury. And dry means no humidity in it. So dry air in the atmosphere at 760 millimeters of mercury. Standard temperature, pressure, dry. Everybody got it? Do I need to repeat it? I will. Let me know.
Yeah, that last
Yeah,
one.
we would just repeat it.
What part? Give me a question.
I know what STPD stands for, but the numbers that you gave out?
Pressure, 760 millimeters of mercury. Temperature, 70 degrees Fahrenheit.
700?
70.
Oh, 70.
A pleasant temperature.
Okay,
70.
okay.
Our equipment is calibrated at 70 degrees Fahrenheit. It'll flow once we get into the equipment. And then dry means no humidity. Okay? Standard temperature, pressure, dry. Standard numbers. What are standard numbers? 1 atmosphere equals 760 millimeters of mercury. What's the temperature? 70 degrees Fahrenheit. What does dry mean? No humidity, no moisture in the air. Got it?
Yes.
All right. Sherry has spoken. She said yes. That's standard temperature, pressure, dry. So what am I saying? I am saying that when we inhale air, it's at 1 atmosphere unless we go to the mountains. And the temperature where everything is really measured is at about 70 degrees and it's dry. So yesterday you went through the upper airway. What's the 3 functions of the nose? Or did you go through the 3 functions of the nose?
Yes.
Yeah. Humidify, there you go. So the air we inhale is dry. The function of your nose is to humidify this dry gas that we breathe. Make sense?
Mm-hmm.
So if you've never appreciated your nose before, now's a good time to appreciate it. It's our first defense mechanism of your respiratory system. Because all the air we inhale is dry. But it must be moist or have humidity in it by the time it gets to the lungs. So that's the function of our nose, is to humidify this dry gas that we're inhaling at 1 atmosphere. Got it? Yes, ma'am.
She said something about 30 degrees Celsius.
What about it?
30.
Well, I was trying to find out yesterday at what point is it automatically.
I don't think 30 degrees, 37 degrees Celsius, that's body temperature. So you got 3 functions of the nose. One is to humidify, one is to warm. And what does your nose do? It takes this dry gas, right? And it humidifies it, it adds moisture, and it warms it to body temperature. So when that oxygen gets to your lungs and is involved in gas exchange, you don't go into shock.
My question I heard was at what point does it start at 37? In the nose or in the throat?
That's the function of the nose, to warm. What does it do? It warms the dry gas to body temperature, 37 degrees Celsius. Right in the nose. And when your nose, if you have a cold, a crud, or whatever, that's when you start getting boogers. So then you know that your nose, something is going on, your nose cannot adequately humidify. You get crud. And then the third function of your nose is to do what?
Filter.
Filter it or get rid of the crud. So that's why we blow boogers. Everybody understand that, right? All right. So now we can understand the function of the nose in relation to standard temperature, pressure, dry. The air that we inhale is dry. And then, like summertime and the humidity is high, it can be overwhelming. It's too much moisture. And we're somewhat miserable. During rainy season or whatever, we feel humidity, right?
Mm-hmm.
All right, yes.
So that's for sea level. What about like different altitudes? Is that
This is just, we're taking it at sea level. If you, let's say, just to give you an example, if you buy cake mix, let's just take a cake. You buy cake mix in the box, it will tell you to add another egg or add another cup of water at altitudes higher than 1 atmosphere.
okay.
All right? Because you're at a different pressure. And mountain climbers have to learn how to breathe at a higher atmosphere. So if you and I went to a higher atmosphere, we would be short of breath and probably hypoxic until we went through some training so our lungs could adapt to a higher atmosphere. Okay, so we're at 1 atmosphere.
I just didn't know if those numbers changed.
Yeah, it changes.
Okay.
Yeah, when you get above 1 atmosphere, this changes.
Okay.
But all of our equipment and what you're going to do, all of our equipment, to make a long story short, is calibrated at 1 atmosphere, sea level. Okay, so that's standard temperature, pressure, dry. Any questions? And now you understand what the function of your nose is to warm, filter, and humidify. It has to humidify because the air we inhale is dry. And then your nose will warm the dry gas to 37 degrees Celsius. And then our first defense mechanism are the vibrissae, our nasal hairs, to get rid of the crud. Right?
Mm-hmm.
All right. And so that barometric pressure is 760 or 14 psi, but most of the time we use this. But this is correct, and I'll go somewhere with this later. So we talked about ventilation. We said ventilation is inhaling oxygen, and ventilation is exhaling waste in our body in the form of a gas of CO2, right?
Yeah.
So now let's go back to inspiration. When we talk about inhaling oxygen, the percentage of oxygen that we inhale, room air, is 21%. The percentage of oxygen in room air is 21%. And it's written in your book, yes, it's written 20.95. We round it up to 21%, so don't get your panties in a wad and tell me what the book says. Room air is 21% or is 0.21. All right, this F, fractional inspired oxygen. Fractional inspired oxygen. It's only a fraction of what we breathe. And what fraction is it? This is where this comes from. It's a fraction. FiO2. So when we inhale room air right now, you and I, we're inhaling an FiO2 of 21%. And now to make a point, a little bit ahead, anytime we administer oxygen to a patient, it's not room air. So when we administer oxygen, regardless of how we administer it, it's going to be somewhere between 22 and 100%. Does that make sense? So if we inhale room air, that PO2, the blood gases that I gave you, and the PaO2 was 80 to 100. Everybody with me? It's based on room air. So that's saying if we inhale room air, our PO2 should be somewhere between 80 and 100 millimeters of mercury, and that's normal. I left a bottle of water up here. I wondered if Miss Pope put it to the side, and she probably threw it out. Any questions with that? So that PO2, 80 to 100, is based on room air. So now you know the FiO2. So what's the barometric pressure? 760. What's the FiO2? 21%. That's what you and I are breathing right now. Also, in room air, we inhale 79% nitrogen. You got some trace gases in there, but they're minuscule, so we really don't count them. So you got 79% nitrogen and 21% oxygen. That's 100%. That's where that comes from. Everybody see that? So what am I saying? I am saying that nitrogen and oxygen are the two major gases that we inhale at sea level or barometric pressure. Now we need this 21% oxygen. Our body needs it. Our body requires it. And it's not a lot. What happens to the nitrogen? Well, the nitrogen is inert when it comes to physiologically in our body, meaning that our body really doesn't use the nitrogen. It's just there. It's a great support system, but we don't use the nitrogen physiologically. What we're relying upon is this 21%. And so we're relying upon this 21%. And so when we look at our blood gas, if it's normal, we're expecting it to be 80 to 100 millimeters of mercury. That's what this is based off of, that FiO2. And this is normal. Does that make sense to you? Any questions? Yes.
I'm not seeing where the PaO2 is coming in, where it comes from.
If you are inhaling room air,
Okay.
and I do a blood gas on you, and physiologically you have no lung complications,
Oh, okay.
your
And
blood
that's-
gas, your PO2 should be 80 to 100 millimeters of mercury.
Okay, so that's normal.
That's normal.
Okay.
Why isn't it, 21?
Why is it what 21?
When the PO2,
If you don't know, I don't know either. You got to ask a question in order for me to answer it.
like that 180 to 100?
Yes.
Is that the 21% of oxygen?
Yes, you inhale the 21% oxygen, and if you inhale 21% oxygen, the partial pressure of your arterial oxygen in your blood is 80 to 100 millimeters of mercury.
That's after the nitrogen?
Nitrogen is inert. Your body doesn't physiologically use it. Okay? Yes.
So on somebody that's hooked up to a ventilator maybe, or someone that's receiving a higher percentage of oxygen, that 80 to 100 millimeters is going to go up,
Nope.
or it goes down.
It could be worse. Yeah, that's why they're on a ventilator, because they need oxygenation. You can have a patient, and I'm just going there to expound upon your question. You can have a patient on 100% oxygen, and their PO2 is only 50. Well, obviously, without knowing any pathology, you know something's wrong. That's why they're on the ventilator, because they need to be oxygenated. So no, don't always assume just because they're on 100%. We would love for everyone's PO2 to be 300, 400, but that's not going to happen. So that just means they need to be on the ventilator longer. Nope.
It can go higher than 100.
What can go higher than 100?
PO2.
Yes, it can go higher than 100, but let me tell you this, if it goes higher than 100, you know as a respiratory therapist the patient is receiving supplemental oxygen. It's not going to go higher than 100 on room air. Make sense?
Yeah.
All right? We're going to start learning how therapists think, what therapists should know. So this is just based on normal. This is normal. So right now, we did a blood gas on any of you. You know you're inhaling room air oxygen, and your PO2 should be 80 to 100. And we know that no one's PO2 probably will be more than 100 because you're not on supplemental oxygen, right? But now if we inhale, this is how we know, I'm getting ahead of myself in the next module. If we have a patient and we take a blood gas on room air, and their room air, FiO2 21%, but their PO2, let's say, comes back 65. Now I know they need some oxygen because room air is no longer enough. So that's when we have to step in and give them supplemental oxygen. And then after we give them the supplemental oxygen, we have to monitor them to make sure they receive enough and then take them off when everything is okay, if they can come off. Does that make sense? Okay, so supplemental oxygen is the oxygen that you will administer, and it's going to be anywhere between 22 to 100%. Got it? And yes, Kyle, you can have a patient on 100% oxygen, and their PO2 can be 50.
Because their body's just not processing it the way.
Something's going on. Physiologically, something's going on.
When when I deal with a patient that their SAT level is say 89%, we're still going to put them on oxygen regardless, because we don't have the capability of checking their PaO2 at that particular
level,
time.
how did you get the SAT level if you didn't check the PO2?
With a pulse ox. With a pulse
Very
ox,
good,
yeah.
very good,
Yeah,
okay.
So I'm just trying to understand, like, when we have a patient that has that level, I mean, we won't really, just on a general basis, we don't have that capability at that particular time to know what their PaO2 is at that time, unless a respiratory therapist comes by and actually
So
checks
you're
them.
speaking from the perspective of your employment now, or as a
Right, as our employment
No,
now.
you wouldn't, but a therapist would.
Right.
Yeah.
So what is the
Okay.
correlation between pulse ox and PaO2?
Don't worry about it right now. We'll get to it on blood gases, yes.
This may be an equipment question, but I was trying.
This may be a what question?
Equipment question,
Oh,
like
okay.
how does the pulse ox actually?
Don't worry about that. We'll get there. Don't worry about that. We'll get there. All right. All right, so everybody understand this? All right. SAT goes with this, but that's blood gases. That's not my focus right now. I'm correlating room air to PO2 80 to 100. All right? All right. So to give you heads up, when the PO2 drops below 80, that means the patient is experiencing, write it down, hypoxemia. Hypoxemia. Below 80 is hypoxemia.
How do you spell that?
HYPOEMIA. HYPOX. I'm sorry. HYPOXEMIA. The emia is in the blood, right? The ox is oxygen. The hypo is not enough. Hypoxemia, not enough what? Oxygen. How do we know? PaO2 less than 80. Make sense? Okay, so what does that mean for you? Supply what? Supplemental oxygen. Hypoxemia. HYPOX EMIA. You all had medical terminology. So when the PO2 is less than 80, that's hypoxemia. So what is that saying? The FiO2 in room air is not enough for that patient. They need supplemental oxygen. Respiratory care to the rescue. Da-da-da-da. Then in module 2, we'll figure out what kind of oxygen or what source of oxygen will we provide for them. All right, any other questions? Okay, back to that hypoxemia. The first step is hypoxemia. It's not enough oxygen in the blood. Then what happens, if it's not enough oxygen in the blood, then it's not going to be enough oxygen that gets to the tissues. And that's called hypoxia. That's called hypoxia. Hypoxia. So there is a difference between hypoxemia and hypoxia. Okay? Hypoxemia is not enough oxygen in the arterial blood. Got it? How do we know? We look at a PaO2. Bam, there we know. And then the next step, if we don't get to the patient soon enough, if it's not enough oxygen in the arterial blood, then the tissues are going to be deprived. And we call that tissue hypoxia. So the first step to a deficit or depravity of oxygen is first hypoxemia, and then tissue hypoxia.
In which case the tissue starts to die.
Yeah, particularly the brain first.
So the human body's a lot like an internal combustion engine, like say in an airplane, when it goes up, oxygen becomes rare, the engine doesn't get enough.
What goes up?
Well, if you take a gasoline engine and you run it up
In the body. I don't know that. What goes up in the body?
well, your acid does, your hydrogen does.
No. I'm talking about oxygenation. Acid is acid-base balance. Oxygenation is another entity.
Yeah,
Acid-base balance and oxygenation are two separate things.
lost myself.
Yeah. Yes.
So when hypoxemia occurs and then hypoxia occurs, does that lead to cardiomyopathy?
If that's the original problem, but not always. It could be. It can cause damage in the kidneys. It can cause anoxic encephalopathy. It can cause brain dead. So no, we have to, that's pathophysiology. We have to look at the origin of the hypoxemia. And that's a good question, because every time a patient is hypoxic or experiencing hypoxemia, it doesn't necessarily mean there's something wrong with the lungs. It just means the lungs can't do or meet the demand. It could be renal. It could be a diabetic. It could be a lot of causes behind it. Yes.
So the PaO2 and the PaCO2 are completely separate?
Yes, ma'am. PaCO2 deals with ventilation. PaO2 deals with oxygenation, and those are two separate entities. We look at it separately, and later on you'll learn how they combine, but they're two separate entities. Ventilation is the movement of air in and out the lungs. That's the only responsibility of the lungs, but it's a big responsibility. Right? Oxygenation. We can control ventilation. Oxygenation is physiologically. It's two parts to oxygenation. External respiration between the atmosphere and the lungs. Internal respiration between the arterial blood and the tissues. When a patient does not get enough gas from the atmosphere to the lungs, that's called hypoxemia. And then when there's not enough oxygen in the arterial blood to be transferred to the tissues, that's called hypoxia. Got it? All right. Any other questions on this? Because I want to move on. Welcome to the world of respiratory care. And therapists understand this. This won't be the last time. You're going to go over it and over it and over it and over it and over it. All right. So now you know that the air that we breathe is room air at a barometric pressure of 760 millimeters of mercury. Is standard temperature pressure dry. It's regulated or calculated at a temperature of 70 degrees Fahrenheit. And now you know the one function of your nose is to humidify this dry gas that you inhale. And you know breathing a room air, FiO2 of 21%, normal PaO2 will be 80 to 100. All right? If we do a blood gas and the patient's PaO2 is less than 80, then we know that they are experiencing hypoxemia. And now you also know they need some supplemental oxygen. And the supplemental range of oxygen in general is between 22% to 100%. Any questions on that?
The range of oxygen is between 22.
Supplemental oxygen, 22 to 100%, meaning the oxygen that you will deliver, that you'll use to provide to the patient. Now, that's general. In Module 2, we're going to break down the apparatuses. All apparatuses can't deliver 22 to 100%. I'm just saying in general so you can understand. Okay, you can't give more than 100%. Any questions? All right. Atmospheric pressure is made up entirely, rounded up, two kind of gases, excuse me, 79% nitrogen and 21% oxygen. This is 100%. And then next Monday, I'm going to show you the pressures. Each one of these exerts a pressure. And together, it will equal 760, but I'm not getting into math today. All right, let's turn to page 888. This is about oxygen. So now we're coming out. We understand that the patient needs supplemental oxygen. Mike, do you see a little tank back there? Over here? Yes. Doyle, will you bring that tank?
Yep.
And I'm not going to move this tank because you all can see it. Thank you. All right. So the supplemental oxygen, that's 22 to 100% that you'll provide in respiratory care. I told you Monday, and I was probably just talking off the top of my head, and I make no apologies, but that's how I flow. All right. I told you the color code for oxygen is green. So you can see that it's green here. You can see this regulator, although you don't know what that is. It's called a Bourdon gauge, is green. You can see this key is green and this is green, different shades of green. And the color code for oxygen is what?
Green.
All right. This is a size E tank. E tank. And you'll touch and feel and rub. Just don't explode and laugh. And this is another tank. You see that it's green. Its top is green. And this is a regular. Both of these are regulators that can be used on it. See all that green? Okay. So it's obvious just looking at it. We haven't learned the names. This can't go on here. It's too big. So this over here is an H tank. These go over here. And you'll learn how to do all this in lab. Okay. So that's an E tank of oxygen, size E. It's small. This is an H tank of oxygen. It's much larger. It's green. How do I know? I can see the color is green, and I also can read the label. And the label will say that it's green. And then over here, these outlets here, it's labeled oxygen in green, and attached to it is a flow meter. And the flow meter says for oxygen use, and it's green. So it's color-coded. So what's my point? The supplemental oxygen that we're going to administer, we will administer either via an E tank, an H tank, or through the wall. because it's an H tank.
Is there like a physical purpose of?
What's the physical purpose of administering oxygen to a patient who needs it? Good answer. All right? So we're going to administer oxygen either through an E tank, an H tank, or through the wall. And the oxygen that we're going to administer will be 22 to 100%. And Module 2, we'll learn the differences in the different apparatuses and what they're capable of. But overall, this is how we deliver supplemental oxygen. Okay? So the first thing you've learned that the color code for oxygen is green. So back to page 888.
Ms. Miller, what does the E and the H stand for?
E and H, sizes.
Okay.
Yeah,
just
different
Sizes.
size.
Okay.
Actually, AAA, AA, and A, perhaps you've seen people in the grocery store or out at the zoo, the park, they have these packs, and you'll see them, they'll have on a nasal cannula, and if you stand close enough, you hear psh, psh, psh. They're receiving oxygen, but they can't carry an H tank or an E tank. So they're AAAs and AAs they can carry as a pack with them. So the smaller the letter, the smaller the tank. The larger the letter, the larger the tank. Okay, so it's just AAA, I believe, to H. And obviously both of these tanks have oxygen in them. It's regulated by FDA. We talked about it in pharmacology yesterday. It's a drug. It's in the form of a gas. And it's regulated by the Food Drug Administration. But this obvious, maybe it's not, I'm not going to assume, you can look at the tanks. What's the difference? Well, obviously, the gas in here is going to last longer than the gas in here because there's more of it. So what we're going to learn, when do you appropriately use an E tank? When do you appropriately use an H tank? When do you appropriately use a wall outlet? That's why you're sitting in class. But all of it is oxygen. All of it, either three of the sources, will provide an FiO2 anywhere between 22 to 100%. Okay?
Can you put that in your house?
No. No. Okay, look at table 37-1. Okay, what I'm going to do is I'm going to go through the therapeutic gases first. Therapeutic gases mean that can be administered, human consumable. That's a therapeutic gas. A therapeutic gas. You see the second label, therapeutic gases. The second one under there is oxygen. That's what we'll administer. And you see it's O2. That means it's diatomic. You have to have 2 molecules of oxygen, and this is one reason why you needed to take chemistry. Okay? And then the color. Oxygen is colorless. You can't see oxygen. You can't see it. All right? You can't taste it, and it has no odor. Can it support life? You bet your sweet bippy. You get somebody with a PO2, let's say 40. That's life-threatening. We know room air is 80 to 100, and now we got a patient with a PO2 of 40. They need some oxygen, and so we're going to give it to them. Now, what I want to tell you in the text, and the text is correct. Sometimes I dispute the text, and if I do dispute it, I'll tell you why. Where it says flammability. Oxygen itself is non-flammable. You get 100% oxygen in that tank, it's non-flammable. However, if it combines with air, it supports combustion. Okay, so oxygen itself, the true characteristic of oxygen is non-flammable. But when it mixes with air, it supports combustion. So now you've learned any patient that you have on oxygen or any room where oxygen is being provided, there must be a no smoking sign. And unfortunately, as a respiratory therapist, I just had the second year students in class on Monday, and I was asking them about their experience. They were in intensive care unit over the summer. Next summer, you'll be in critical care. They were in intensive care unit, and one of them was telling me that they had a patient in the burn intensive care unit, and I asked why. At home, on oxygen, smoke. Poof. And they probably won't recover. Okay, so oxygen supports combustion. And so everywhere you provide oxygen, there should be a no smoking sign up. And it's going to be important, particularly if you have patients that go home on oxygen, that you clearly emphasize that they cannot smoke or light matches around oxygen because it supports combustion. Okay? Any questions with that? So it's odorless, it's tasteless, we can't see it, but it's regulated by FDA. And FDA said that I think it has to be 99.5% pure when we administer it therapeutically. And it will support combustion. Yes, ma'am.
That's I'm not trying to point, but a lot of people use those
Go ahead.
e-cigarettes. They're like electronic cigarettes.
What about it?
If you have a patient and they really want to smoke and they want to use that, would that aggravate these systems?
If you have a patient that what?
Really wants to smoke or something, can they use that e-cigarette around that? Or?
Yeah, the electronic cigarettes.
No, because it's got a battery.
Yeah, it's
I
got a
don't think that
No.
didn't start
real
on
powerful
the
battery.
ignition,
No.
yeah.
And if you see them, you should tell them, no, don't use it. No. Okay, the next one, I'll go back up, is air. The color code for compressed air. Now, compressed air is air that we inhale. I'm sorry, we don't inhale compressed air, but compressed air is the same kind of air that we inhale. But it can be in an E-tank, and the color code is yellow. So it'll be a yellow tank just like this. It'll have compressed air on it, and it will have a yellow regulator. It could be an H-tank of compressed air. It will be labeled compressed air, and the tank will be yellow. Make sense? What is this? Compressed air. This is a flow meter. It's labeled yellow. That's its color code. It says compressed air, and here it is right here, air. Okay? And somebody is saying their head is rolling. Well, why would we administer compressed air? When we get to that particular module, I'll explain to you. There's therapies. Pharmacology is one. We can administer a drug through a small volume nebulizer, but we don't have to give the patient any oxygen. We just want to administer the drug. Well, what we'll use is compressed air. And the compressed air will just provide a source for the drug to be aerosolized. And we're not providing any additional oxygen because they don't need it. They need the drug, but they don't need the oxygen. That's an example of when we'll use compressed air. Does that make sense? Yes.
So you're talking about a healthy person that has the PaO2.
May not necessarily be healthy, they just don't need oxygen.
it.
Yeah. Everybody sick doesn't need oxygen. Yes, sir.
So like a puffer or something in that?
No, not a puffer,
That's
not an MDI, not a spacer, because that's no oxygen source at all.
Okay.
I'm talking about a small volume nebulizer where we have to provide aerosolized treatments.
Okay.
Not an MDI, patient can do that on their own.
Okay.
Not a DPI, dry powder inhaler, they can do that on their own. I'm talking about they're in the hospital and they need a particular drug, pharmacological agent that you're going to administer, but they don't need the oxygen. Yes. Oh, you're just scratching. Okay. Did I see hands over here? Okay, that would be an example when we would use compressed air. Now, to be honest with you, I'm going to be very practical. You probably won't use an E-tank and an H-tank of compressed air. Your patient will be in the hospital and there will be an outlet along with the oxygen. You all that work see these together along with the suction. and you will use that compressed air outlet to administer your small volume nebulizer treatment without providing additional oxygen. Now, if your patient is on supplemental oxygen and they need this particular drug, then you would use the oxygen source. Does that make sense? All right. So we're going to learn what therapies are, why we use them, when we use them, and what's appropriate and what's not appropriate. All right? Okay, so we've gone through oxygen. The color code is what?
Green.
Gone through compressed air, it's what?
Yellow.
All right. And of course, compressed air supports oxygen. Compressed air is comprised of 79% oxygen and 21% oxygen. I'm sorry, 79% nitrogen and 21% oxygen. It's the same thing as room air, except it's under high pressure. And I guess I need to go there right now. When I say high pressure, our atmosphere pressure is 760, right? Or 14.7 psi. Yes?
Yes.
All right. The pressures in these tanks is great. A full tank, whether it's an E tank or H tank, is generally about 2,400 psi.
Wow.
It's under pressure. This is when we use the PSI. Everything else we use metric system. But both of those tanks, that little bitty E tank and that great big H tank, they're under pressure 2,400 psi. That's much greater than atmosphere, isn't it? That's why you're sitting in class, and that's why in lab, Ms. Pope will walk you through how to handle these tanks, because they're under pressure. And if you don't treat the tanks with respect, they will shoot off like missiles. And they can't knock a hole in the wall. Plus, Lord forbid, if it comes in any contact with any electricity, it can explode. So when these tanks are full, they're under high pressure. A full tank can be 2,400 psi. That's the pressure. And that is much greater than atmosphere, right? Mm-hmm. Okay. So then we have equipment just for these tanks, such as this and this. These are called regulators. The purpose of a regulator is to reduce this high working pressure in these tanks down to a working pressure where we can deliver our therapy, whether it be compressed air or oxygen, to a patient, and it's compatible. So the purpose of regulators, write this down. The purpose of a regulator, can I erase this?
Oh, yeah.
Thank you. We're going to identify and name the regulators, but not yet. Is everybody understanding what I'm saying? This is the rudimentary, the fundamentals of respiratory care. Because we don't want you to drop the tank on your foot, we don't want you to break your foot, and we don't want the tanks shooting off like missiles. The purpose of the regulator, remember, if the tank is full, it can be 2,400 psi. If the tank is half full, it could be what, 1,200 psi. That's still greater than 1 atmosphere. So when somebody asks me about why are we talking about 1 atmosphere, the point is when you deal with these tanks, you're dealing with pressure greater than atmosphere, much greater than atmosphere. Make sense? So the purpose of these regulators, whether it be a little tank or a big tank, is to reduce that high working pressure down to a 50 psi. So all of our respiratory care equipment will reduce that high working pressure down to a 50 psi. Got that? And what do we call that? We call that pneumatically powered. Pneumatically powered. Pneumatically. What does pneuma mean?
Air.
That's Greek. Air. So now you know if I say, what is the pressure of a pneumatically powered piece of equipment? You're going to tell me what?
50 psi.
50 psi. If I say, what is the working pressure of all respiratory care equipment, what are you going to tell me?
50 psi.
50 psi. That's the purpose of regulators. These are regulators. We're going to get through the different kind of regulators. But the gas this is attached to the tank. And inside here, it reduces that high working pressure down to a 50 psi. And then that 50 psi is delivered. Also, even this outlet here, it's pneumatically powered. So even here, this will come from the hospital. It's 50 psi. So when I take this regulator and attach to the tank, or I take this airflow meter and attach here, I know that it's a working pressure of 50 psi, and that's standardized for all of our respiratory care equipment. So anything that has to be attached to gas has a working pressure of 50 psi. And you know what? I told you that atmospheric pressure was 14.7 psi, right? So even 50 psi is greater than 1 atmosphere. Now what's great here in this lab, I had this design that it's at elbow level. But you little petite ladies, be careful, because sometimes the oxygen source that can be higher than you. And if you don't know how they work the equipment, that flow meter come out, hit you in your forehead. And it's coming out at that 50 psi. And you do it once, you won't forget anymore. Ask me how I know. It was 50 psi in the 70s too. All right. So when we talk about pneumatically powered, we're talking about all high gas flow systems, or all high, not gas flow systems, all high working pressures being reduced down to a 50 psi. Okay, so all of our equipment that requires that is calibrated at 70 degrees Fahrenheit, and the pressure is reduced from whatever it was to 50 psi. And we call that pneumatically powered. Yes.
So when you say working pressure, you mean the pressure of the tank?
No, working pressure is 50 psi.
PSI?
Working pressure means our equipment has broken the high pressure down to make it deliverable for human consumption. If I tried to put you on an H tank without a regulator, you couldn't take it because the pressure would be too high.
Like blow up like a balloon?
You wouldn't, it wouldn't even blow up because you wouldn't be able to allow any of the gas to reach your lung. You turn away. Because we inhale at 1 atmosphere. This is well above 1 atmosphere. You couldn't take it. So it's the responsibility of the regulators to reduce it down to a working pressure of 50 psi. So when we deliver our supplemental oxygen, whether it be 22% or 100%, we're using a pneumatically powered piece of equipment. And so you know pneumatically powered is working pressure. Working pressure for our equipment is 50 psi. Still well above atmosphere, but it's come down tremendously. And what kind of equipment does that? Either regulators for the E tank, the H tank, or it will be piped in oxygen source. And if it's piped in through the hospital, it's still a working pressure of 50 psi. Okay? Everybody got that? All right. All right, so we did air, we did oxygen. Helium and oxygen, that will be a gas you'll learn about. Helium, the color code is brown. I think it's a...
This is chart.
Yeah, 37.2. Turn to page 891 and you'll see the color codes. Helium itself is brown, and then if you look down, you'll see helium in O2. See it? Helium is brown, oxygen is green. We call that heliox. HeO2, heliox. We as respiratory therapists use that as well. to administer therapy. The molecular weight of helium is much lighter than oxygen. The gram molecular weight of helium is 4. Oxygen is 16. So helium will flow faster than oxygen. So sometime in therapies you will learn when to use that and when not. We use heliox tanks. And so if it's heliox, the majority of the tank will be helium and then a percentage will be oxygen. So that tank, we don't have any in here, but that tank would be brown and green. Okay, so that's helium. All right, and then back to the therapeutic gases, carbon dioxide. Carbon dioxide, the tank is what? Gray.
Great.
Now, we as respiratory therapists won't use carbon dioxide, but they use that therapeutically. They could use it in anesthesia, and they can use it probably in a lab where they're doing diagnostic testing, microbiology. We as therapists won't use that, but still, nevertheless, you just need to know the color code. Now, over here, somebody's going to ask me, well, if the color code for carbon dioxide is gray, and you said the color code for oxygen is green, why do I see this gray? Well, the reason you see this is because when we order our oxygen, the company that we use, they realize that this is not going to be a gas that's going to be used or administered in a hospital. So to give us a discount, if you will, we tell them, provide us with oxygen, label it, and we don't care what color it is. Okay, so technically, if this were in the hospital, I would say this tank is filled with probably 95% carbon dioxide and 5% oxygen. But for purposes in here, yes, the tank is gray, but it is all oxygen.
So would it normally be green like page 6?
Yes, it would be all green like that. Okay, everybody got that? This is because we got a discount. We get a discount when we purchase things because it's for educational purposes and it's not going to be used therapeutically on patients. Okay? I know somebody's head was turning already. Well, why is that tank gray? That's why. All right. And nitrous oxide, NO, nitrous oxide is what? Blue.
Blue.
Once in a while, if you work in that area, particularly in the neonates, we will administer nitrous oxide therapy, and that will be discussed when you get more into pathophysiology. So the focus now is the color codes for the tanks. All right, and who regulates that? The Compressed Gas Association, CGA. You can read this in the book. What I'm saying is all in the book. The Compressed Gas Association and the National Fire Protection Agency have collaborated, and they've come up with these safety standards. So we can't inadvertently take an oxygen flow meter and mistakenly think we're giving a patient 100% oxygen when all we're really doing is giving them compressed air. Could you imagine a patient in a full-blown cardiac arrest, not breathing, and we make a mistake, which we wouldn't, I'm just making a point, we make a mistake and take our oxygen flow meter and connect it to compressed air? All they would just be getting is just air. And so surely they would die. So with the Compressed Gas Association, along with the National Fire Protection Agency, we say, oh, we got to put some safety systems in place. So they put safety systems in place so we can't inadvertently connect the wrong kind of equipment to the wrong source. Does that make sense? Mm-hmm. So that's why all your therapeutic gases and your anesthetic gases or what have you are color coded. They have to be color coded. So if we're using a tank of cyclopropane, which we wouldn't use, but wherever they use it, it's color coded. And everything that attaches to it is that same color. So we can't make a mistake. Okay, so the Compressed Gas Association said we have to have safety systems in place. So here we go. They said for E-tanks, it's called PIS, Pin Index Safety System. Right now? PIS, Pin Index Safety System. E-tanks, piss. Woo, I feel that air going over here. We need to have on a sweat. Maybe that's you that need to have on a sweat. E-tanks. What we have on the E-tank is a regulator. Remember I told you I should say a gauge. This and this are the same thing. This is green, this is green, this is green, this is green. I'm going to leave this on here. But what we have here are pinholes. And these pinholes are for oxygen. Okay? So if this was a tank of carbon dioxide, number one, I'd look at the color, and I see it's not green. It would be what color if it was carbon dioxide? Gray. All right. This would be gray. This would be gray. And the pinholes, there's two little holes on the tank. The pinholes would line up with here. So these are the pins. And so it's the pin index safety system, PIS. So let's say this is an oxygen regulator, and I don't know that it's an oxygen regulator, and I try to take this regulator and put on an E-tank of carbon dioxide. It's not going to fit because the pins are not going to line up with the holes in the carbon dioxide. I shouldn't say holes, the orifices on the tank. So it's the pin index safety system. In lab, you all can take this off and see. These little things here are called Bourdon gauges. Write it down. B-O-U-R-D-O-N. B-O-U-R. I think I'm spelling it. Or it may just be B-O-R-D-O-N. It's in your book. Bourdon gauge. What's the purpose of a Bourdon gauge? Number one is to take the high working pressure in the tank and to reduce it down to 50 psi. Make sense? That's called a Bourdon gauge. When do we use Bourdon gauges? On E-tanks. So both of these that I have in my hand, and come up if you can't see it, are Bourdon gauges. How do I know? I also know that it's the pin index safety system because I see these two pins. And these two pins are going to line up, and they're in here. Have Miss Pope take this off for you guys, and you'll see the placement of the hose. Let me see. I see one for the H-tank. Yes. Look on page 900. Figure 13, I'm sorry, figure 3714. There they are. So every respective gas has pinholes. And the pinholes are important, but I believe oxygen is 2 and 5. I'm not going to ask you that. Who cares? As long as your regulator attaches. And if you inadvertently took a Bourdon gauge that wasn't for an oxygen tank, it wouldn't fit because the safety system, the orifice on the tank wouldn't align with the pins here, and so it wouldn't fit. It would be like taking round pins trying to put in a square hole. Not going to work. Okay, so that's the safety system, the pin placement, where the pins are placed. Is PIS, Pin Index Safety System. These are the pins. And what is this called? A Bourdon gauge. What's the purpose of a Bourdon gauge? To take the high working pressure in this tank and reduce it to 50 psi so we can now use the tank and deliver whatever it is we want to deliver. Any questions? All right? Yes?
If you know that the tank is almost empty,
You change it.
or you don't think that
No, you change it. We'll get to that. This is the H tank. I'm not moving it. The H tank is AS. American Standard safety system. Sounds like we're cursing, that's why I closed the door. Yes, let's do it. ASS. American Standard Safety System. That's for the large tanks. Well, I can just look. Both of these are for large tanks, yes? You sure? No, they're not. I see pins here. No, they're not. I see pins right here. It's big, but this is for an E-tank. See these pins? Let me pass this around. Even though that's a big fella, that's for a size E-tank because I see pins. The American Standard Safety System for H-tank are threads. This is for an H-tank, and this is what you're going to learn in lab to be able to recognize. Don't be fooled just because that regulator is big. It's still for a size E-tank because it has pins in it. See it? This doesn't. This is American Standard Safety System, and how I know it's for an H-tank, it has threads in it. We take this top off here, and I'm not going to do that. You'll do that in lab. I'm not going to steal Miss Pope's thunder. You take this top off, but when you take this top off, you'll see the outlet has threads. And those threads match these threads. So this is the American Standard Safety System.
Is it still called a board-on gauge? It's different.
This one is. I'll explain the difference. Both of these are for large tanks. How do I know? I see the threads. I see the threads. Both of them are. I see these are green, and I see green here, and it says oxygen on it. I see green here. I see green here. I see green here. So I know these are for oxygen, but they're a little different. And I'm going to explain the difference, not now, but I'm going to tell you. But nevertheless, my point here is that they're the American Standard Safety System. So PIS are for size what? E-tanks. ASS is for size what? H-tanks.
Is there a special name for those, like?
I'll get to them. Piped in oxygen in the hospital. This diameter index safety system. Diameter index safety system. See, this is called a flow meter. Diameter index safety system. This is a flow meter. Flow meters attached. We don't need a regulator or a board-on gauge with that because the hospital will provide the worker pressure. So this is diameter index safety system. It's for piped in oxygen in a hospital or any institution where that's piped in. So all we need is, this is a flow meter. And it only will go into a diameter index safety system. So we need those gauges for size E tanks and H tanks. And you need to know how to put them on. You need to know how to take them off. You should be able to identify them. And then you're going to learn in lab how to transport this tank. And so it doesn't matter if you work in respiratory care and you weigh 95 pounds. You should be able to move that tank, a full tank, and transport it from one place to another if you have to. You all don't have to do laborious work like we had to because most places is piped in oxygen. But you may have to transport your patient somewhere. And you need to know how to use it. Yes?
Do you only use a flow meter when it comes out of the
Only.
disc?
Mm-hmm. Now, she asked a very good question. I have a flow meter attached to this. But this is not piped in. This is what kind of safety system? ASS, and I know it's for what size tank?
H.
All right, so this is a flow meter for this, piped in oxygen. I see a flow meter here, but I know this is not a flow meter that I could attach directly to this. I know this safety system is ASS So I know this goes on an H tank. Everybody see the difference? All right, I'm gonna pass it around. And you'll touch and feel it in, here. Touch and feel it in lab. Any questions with that?
Did you say it was a gauge?
Hmm?
The disc? The gauge?
This is 50 PSI. There is no gauge on this.
Okay.
Yes.
So in other words, what's happening is when you use an AS or a test with a gauge, you're reducing it down to where you now can use that flow meter. That's why it's attached on that other side like that?
You don't necessarily, yeah, that's one way to look at it, but you don't necessarily need a flow meter. When the gauge is reducing the pressure, it's reducing it down to 50 PSI for where our respiratory care equipment is calibrated so that it can function.
So you can attach it?
Yeah.
Okay, you don't necessarily have to have.
No, mechanical ventilators are not attached to a flow meter. The outlet goes directly into the piping goes directly into the oxygen outlet.
Okay.
Yes, yes.
The flow meter is what controls, after you get it to 50 PSI, that's what the treatment's gonna be, you're regulating the flow
Yes,
from there to the
and I'll get,
patient.
yes, that's
Okay,
it.
I just wanna make sure I understand.
Okay, so we've learned about ass, piss, and this, yes.
Since there are more gases and mixtures than connectors,
Say what? What do you mean? I hear you, but I don't hear you.
because there's 62 gases and mixtures as far as the connectors, so there's less connectors than the tanks themselves.
Where,
I have from the book,
what 62 gases? Where are you? What page?
899.
899.
Says there are only 26 connections.
Wait a minute, let me find where you are. Okay, 899, and where?
Second paragraph under AS.
Oh, it says because there's only 26 connections listed for the 62 gases and mixture. Each gas may not have a unique connection. Some of that doesn't apply to us. That's
Okay, that was my
overall.
question.
Some of that's laboratory gas, some of that's anesthetic gases, and some of it's therapeutic.
Oh.
But for us, we'll use the oxygen, we'll use the heliox, and we'll use the nitrous oxide.
For us, it is unique.
Yeah, for us it's unique. Yeah, for us it's unique. Yeah. Yes. Okay, any questions? You've learned about what we had on the board. You've learned about the tanks are under high pressure. And now you know the purpose of regulators and gauges is to take that high working pressure and reduce it to 50 PSI. You know about a size E tank, an H tank, and then the 50 PSI disc outlet. You know about safety systems. You know Compressed Gas Association and the National Fire Protection Agency have regulated this. So we don't blow our food cells up as well as our patients, right? Because if, you know, of course, it can happen. You didn't mean to, but it can happen. But with the Compressed Gas Association, it's not going to happen. Because you know what? It's not going to fit. You can't take a square peg and put it in a round hole. And so, because of the safety systems. And then, how do we know? How do we know what the gas is? Number one, we identify its color code. Number two, you know its safety system. And number three, read the label. That's the 3 ways to identify a gas. Look at its color code. Identify its safety system. You better know this because I'm not standing here talking to myself. And read the label. Identify the color code. Identify its safety system. And read the label. Want it again? Color code, safety system, read. So if you have the safety system, you know what size tank it is. Yes? All right. Any questions? So I definitely want you to know color code for compressed air. Thank you. Oxygen. Helium. Heliox. HEO2. And nitrous oxide. That's NO. And they're right there in the book.
Helium, and nitrous oxide.
Any questions?
Under module 1 for number 9, we didn't so much go over quick connect systems. Do we just need to know the other?
Quick connect systems are these. It's different kinds. Quick connect systems are a different type of flow meters. I only have one kind of quick connect system, but the hospital may have different kinds. Quick connect systems are for this.
We still know that one.
A lot of places have standardized quick connect systems. If you turn to page 892, you'll see the different size tanks.
Okay, what page?
892, under figure 37.4, cylinder sizes are identified by letter designations. So let me give you this. What we have in the book is AA, but there's a AAA. That would be for home care. So I'm just going to go by what's in the book. So AA to E. AA to E would be piss. AA to E would be piss. And so that means it would have the pinholes, right? AA to E would be the safety system of piss. Your size G and H would be what? Ass. Got it? Now, I'm taking all the stuff that's in the book and I'm making it succinct. That's what Kathy Miller does. You can read the text, but I'm making it succinct. And then the only time you will see this is when a facility has piped in oxygen.
And then all you have to do is use a flow meter. 'cause it's
Use a
already
flow
in.
meter or whatever you're using
It's
and
already
connect it.
See, size H and G are,
Ass.
let's see,
Why not? It's American Standard Safety System.
I know.
Just say ask.
You're not pointing to your ass, you're saying ass, American Standard Safety System. It's 3 S's, not 2.
Thanks for that distinction.
Yes, we're talking about tanks, not your tush. Okay, any questions on anything I've gone over? That's why I said I'm going to give you a PowerPoint, because some of you probably think I'm all over the place, but I go right to what you need. You've learned a lot today. You've learned a lot today, and you're expected to know it. And again, this is theory. I introduce it to you, but you do it, touch it, feel it, whatever, in lab. Yes, sir.
As far as, I know you said nitrous oxide, but you know there's nitric and nitrous. And then on the color code chart.
I want NO.
You just want NO, right?
NO.
Okay.
We use NO.
All right. No problem.
So you want us to know the blue tank, right?
Yes.
For NO2.
Yes, because
NO2,
we use it. Yes. Yeah, we use it. In
But-
Module 2, we'll talk about when we use it, but I want you to know. Yes.
Okay, on the chart in the book on 891, it just gives N2O, and it's just blue,
Yeah.
and then NO it doesn't have it. It's not listed.
It's still blue.
It's still blue. Okay.
It's still blue.
All right.
And guess what? If we're not sure about the color code, what are we going to do? Read the label.
Okay.
Okay, but it's still blue.
Okay.
All right. Okay. So the characteristics of gases. Let's go back to page 888. And you'll see that I'm not making this stuff up. At the bottom it says characteristics of medical gases. I'm primarily going to focus on oxygen. It says oxygen is colorless, odorless, transparent, and tasteless. It exists naturally as a free molecular O2 and as a compound of host with other compounds. Oxygen consists, do we care, 50% of the weight's Earth, but all living organisms need it. And so how much oxygen do we need? 21%.
21%.
What's the FiO2 that we inhale, room air? 21%. At standard temperature, pressure, dry. Now you know what that is, right?
Yeah.
Standard temperature pressure dry. It means that the atmosphere air that we inhale is dry. And it means that it's the responsibility of our schnoz, our nose, to humidify and warm that dry gas. So you have a plethora of of capillaries in your nose. And when the dry gas comes in contact and goes through the concha, the inferior, superior, middle, and inferior turbinates of concha, it's a smooth flow. It's a laminar flow. Some goes up, some goes straight, some goes down. So all of the dry gas can come in contact with your nose, and it will warm the gas and then add moisture. Because it's got to be our body is about 70% water. That dry gas has to have humidity in it and be warmed by the time it reaches the lungs for external respiration, right? Okay, so standard temperature pressure dry, and these tanks and that outlet is based on the same thing, standard temperature pressure dry. All right? All right. However, the pressure is much higher in those two tanks, and nevertheless it's still higher when we talk about pneumatically powered, because atmosphere is 14.7 psi. Pneumatically powered is 50. So that's still a lot. But that's the working pressure, whether it's a mechanical ventilator, whether it's non-invasive positive pressure, or whether it's just a nasal cannula oxygen. It's all the working pressure at 50 psi. Okay? Standard equipment in respiratory care is standardized, calibrated at 70 degrees Celsius at a working pressure of 50 psi. All right. All right. So we look at this oxygen, and oxygen has a density, meaning it's heavier than air. Air is 1.29 grams per liter. Oxygen is 1.429. So oxygen is a little heavier than air. All right? I'm going to skip that bottom part and go to the right. Oxygen is non-flammable. I told you that. Oxygen itself is non-flammable. But when it comes in contact with air, boom, it's combustible. But oxygen itself is non-flammable. And I hope nobody has experienced this. You're pretty much a peace-loving, easygoing person. And I'm like that. I'll fight if I have to, and I'm not going to let anybody step on my toes. But I married a man when I was younger. And he brought out the green-eyed monster in me, and I was combustible. So that's how oxygen is. It's just by the grace of God I'm still here, because I had made up in my mind I was going to kill him. And so I've never birthed any children, but I have a 23-year-old granddaughter. I raised his granddaughter. She belongs to me. She's 23 years old. And many a day I cried and said, God, why? Why? It was for me to learn love, unconditional love. And then I didn't ask for her, but I got Paulette out of it. So anyway. So you know how you are. Maybe some of you haven't experienced that, but that's my analogy. Oxygen by itself is okay. But if it mixed with air, you got a problem. And that's how I was. He brought out the green-eyed monster in me. So it's taken me a long time to learn how to manage my anger. But I think I'm there. Don't test me, though. Please don't test me. All right. So standard temperature pressure dry. So oxygen by itself is non-flammable, but it greatly accelerates combustion. Running speed increases with either an increase in oxygen percent. So it's saying more oxygen, the greater danger. So it's 100% oxygen in both these tanks. And it doesn't matter if the tank is completely full, half full, or almost empty. The content in it is still 100%. Does that make sense?
Mm-hmm.
Okay, and so if we don't handle the tanks correctly, number one, if you accidentally drop it over, you don't want to drop it on your foot, because it can break a foot. It can hurt. And then if it hits the wrong thing, it can explode. And so in lab, you'll learn how to manipulate and handle the regulators and change the tanks. All right? Okay.
Ms. Miller?
Yes.
I was reading a little bit about the difference between liquid oxygen versus gaseous oxygen. And I was just curious, it did appear from what I was reading that most of the time the liquid oxygen is used in a big facility.
Absolutely, as a
So
reservoir.
We usually won't be in
No,
contact.
you won't be responsible. That's a good point. This is in a gas form, and this is a gas form. But it's regulated by FDA. All facilities that have piped-in oxygen, they must have a source of piped-in oxygen, but as a backup resource, they must have liquid oxygen as well. So like say in instance of disaster or something happens, those patients that need oxygen, particularly those patients like an intensive care unit on ventilators,
Yes.
they got to provide the oxygen.
Okay.
It's got to come from somewhere. And so the liquid you guys won't really be dealing with. What you'll be dealing with are the gases under this high pressure.
Okay.
Very good question. Yeah, I was going to get to that, but I answered it. Okay. All right. All right. Any questions on anything we've gone through? All right. I'll go back to the production of oxygen on, today is Wednesday, on Monday, but look at page 890, storage of medical gases. It says medical gases are stored either in a portable high-pressure cylinder, and I talked about that high pressure, right? A full tank can be 2,400 PSI. That's that high pressure, well above 1 atmosphere. Or in large bulk reservoirs. Bulk reservoir systems require a separate distribution to deliver gas to a patient, and that's the facilities. They have to have a backup. And you won't see that when you walk in the hospital, but in the back somewhere, I don't know how many feet, but if you ever have an opportunity, you can go in the back or ask your clinical instructor or the department, where is the supply, the reservoir? It's somewhere, and it's protected. Okay, it's protected, and I'll talk about that protection. Okay, let's go below gas cylinders. The containers used to store and ship compressed or liquid medical gases are high-pressure cylinders, and you understand that now, well above 1 atmosphere, right? The design, manufacture, transport of these cylinders are carefully controlled by industrial standards and federal regulations. Gas cylinders are seamless. They don't have any seams in it. Why? Because gas could seep out. So they're seamless. Gas cylinders are seamless steel, and they're classified by the U.S. Department of Transportation according to their fabrication method. The DOT Type 3A cylinders are made from carbon steel, and the DOT Type 3A containers are manufactured with a steel alloy temperature for a higher strength. So, what you're going to go through in lab are markings, and what you can see here on the top of page 891 are the markings. And I'm not going to go through the markings, but you will go through the markings with Miss Pope in lab, because they're actually there on each tank. All tanks have markings, and those markings mean something, okay? All right, now let's look at figure 37.3 and look at the diagram to the right. I'm sorry, look at the diagram to the left. I'm saying right, holding out my left hand. What size tank is that? How do you know it?
The manufacturer mark.
That manufacturer's mark is not telling you the size of the tank. That manufacturer mark, it could be Hall.
Oh, okay.
Okay.
I did look at this.
What size is it? How do you know it's an E-tank?
Oh, yeah.
Did you hear this young lady? She says it's an E-tank because she sees 2 pinholes.
Right.
She's correct. See the 2 pinholes?
Yep.
That's how you know it's an E-tank. That H, that could be M for Miller. I can manufacture it. So don't look at the manufacturer's mark. That's not indicating. Okay? That's just saying what their emblem is. It's an E-tank, because I see those pinholes. Now, I'm not going to do that to you on a test, but these are little things you as a therapist would want to know, yes.
I mean, could that be like E to double A?
Yeah,
but
just to make a point, we
we
just
use
going to
E,
use E and H.
Gotcha.
Double A, you're not going to use. That's for people at home. You're not going to come in contact with that unless you do home care. So for standardization, I'm just going to use E and H. G-tanks are used in laboratories. You probably won't come in contact with a G-tank. So we're just going to stick with E and H. Okay? All right. So you'll go through the markings with Miss Pope in lab. All right. And what else do I want to say?
She's wearing the black hoodie.
Yeah, I have mine too. I need to stop. Let's stop right there. She has on her jacket, I brought mine. What it says is respiratory, I'm sorry, yes, it says respiratory care. This is